A satellite of mass m revolves around the planet A in a circular orbit at a constant distance d from the planet's surface. The planet has a radius r and a mass capitalized M. Assume no other external forces act on the satellite. Part A. 1. Determine the magnitude of the gravitational force acting on the satellites at this position. 2. Determine the gravitational acceleration experienced by the satellite at this position. Parentheses. Assuming no other celestial bodies exert forces on the satellite. So in this type of situation, we don't really need to draw a free body diagram because, the satellite's outer space, right? So the only force that act on it is the gravitational force by the planet A over here. So over here we have to use the formula for the universal gravitational formula. Fg is equal to G. This big G is actually a constant. It's approximately equal to 6.67 times 10 to the negative 11th power. It's Fg is equal to G times m1 times m2. These two are the mass of two different objects over the distance between them, the square of the distance between their center of mass. So in this question, we can just plug the value in. It's equal to G times what's the mass of the satellite? It's equal to lowercase m, right? So we can write it down. M times the mass of the planet is capitalized M. We can write times M over the distance between their center of mass. Don't be tricked by D. D is the distance between the center of mass of the satellite. That's no problem. However, it is the distance between the center of mass of the satellites to the surface of the planet, which is not the distance between their center of mass. The actual distance is supposed to be this part. So the distance we can just write d plus r squared. So easily, this is the answer for part 1. For second part, determine the gravitational acceleration experienced by the satellite at this position. Since the satellite is like there's a gravitational force that act on the satellite, right? What is Fg equal to? In the most basic way. It is equal to mg, right? It was equal to m times g. I will actually write g1 because it's not 9.8, obviously. Now we have to determine which mass we can cancel out. Because we're analyzing the satellite, right? So the mass over here is the mass of the satellite. This is also the mass of satellite, so we can cancel it out. Which we can easily get the gravitational acceleration, g1, will be equal to g times big M, the mass of the planet, over d plus r squared. This is your answer for part 2. Part B. If the satellite's distance from the planet's surface becomes 3 times its original value, determine the ratio of the new gravitational acceleration to the original gravitational acceleration. Part 2. If the mass of the planet becomes 4 times its original value while the satellite's distance from the planet's surface remains the same, determine the ratio of the new gravitational acceleration to the original gravitational acceleration. So let's short it down. This is asking you the new g, the ratio of new g to original g, g1, the g1 we get from here. And this one is asking you the newer g, the ratio of newer g to the original g1. We can just straight up use a conclusion from part A. The gravitational acceleration constant is equal to big G times the mass of the planet over d plus r squared. So for the first part, which one is becoming bigger? the planet's surface, the distance between from the planet's surface to the satellite is 3 times bigger. So now the new G is equal to G times M over 3D plus R squared. Now it's asking the ratio. We can obviously using the ones method. This is 1, this is 1, this is also 1, this is also 1. However, the stuff inside the parentheses changed. So we cannot use it as ones. Also, we cannot determine the actual ratios because we do not know the ratio of D plus R to 3D plus R. So when we're doing the ratio, these two will not exist. So the ratio will be Gn over G1 is equal to 1 over 3D plus R squared over 1 over D plus R squared, which we can get the final answer will be D plus R squared over 3D plus R squared. That's your answer for part 1. For part 2. Now it says the mass of the planet is 4 times its original value. So now M becomes 4M. Still, we can write the expression, right? For newer G, it's equal to G times new mass of the planet, which will be 4M, over the distance doesn't change, right? The distance between the center of mass doesn't change. It's still D plus R because, yeah, only part A changed the distance between them. Part 1 changed the distance between them, so it's still R plus D, D plus R squared. Still using the months method, G is 1, M is 1, D plus R is 1. G is 1, M is now 4, no longer 1, D plus R is 1. So the ratio, newer G over G1 will just be 4. These two are the answers. This is for part 1. This is for part 2. Let's jump straight to the next one.